The matter case has made big progress. We know that matter is all around us. It can be as small as the particles that make the tiny cell in our skin, or as large as the whole galaxy. Anything that takes up space and has mass is called matter. At the most fundamental level, matter is composed of elementary particles known as quarks and leptons. Quarks combine into protons and neutrons and along with electrons form atoms of the elements of the periodic table. Okay, now that we do know what is matter, let's go on to a new case that recently came up and is confusing the world. It is similar to the one mentioned before and is called dark matter. We interview some experts to explain what's the matter with this new case.
This is indeed a big mystery that physics is currently trying to solve. We are very happy to have discovered the fundamental constituents of normal matter, but its behavior revealed some confusing phenomena that led us to the assumption that there must be more than just the matter we know.
One strong indicator is the rotation velocity of galaxies. When looking at the mass distribution in some galaxies, the rotation velocity should decrease with distance from the center, but instead we observe an increase in the rotational velocity. Hence, there must be more matter that we are unable to see. And it's hard to get information about something you cannot see and that barely interacts with the normal matter. But as we know, scientists are good detectives and they are trying to solve the case.
Here are the main things that we know about the dark matter case so far. Firstly, there is approximately 5 times more dark matter than normal matter present in the universe. Secondly, dark matter can interact gravitationally with normal matter, but doesn't seem to be affected by electromagnetism or the strong and weak nuclear forces. And thirdly, unlike normal matter, dark matter can't collapse to form denser structures. We want to discover different ways that dark matter can interact with normal matter. But most importantly, we want to detect these interactions. Let's see how we can do this.
Now that we know what dark matter is, we're going to talk about how we can detect dark matter in our research. So what we're going to use is something called fundamental oscillating constants, which are constant values that make up the physics of our own universe. One constant value we're going to look at is called fine structure constant. And it is funny to say that a constant value does not always have to stay constant, it is so-called. An alpha value, so-called fine structure constant, is oscillating due to the interaction with the scalar field of dark matter, which is shown in this equation, which is phi. And these two observations show that the fundamental constants in our own universe can actually oscillate due to natural causes. And this Lagrangian, which is the interaction between our own classical system and the field of dark matter, which is this phi value, shows that dark matter can actually contribute to the oscillation of our own universe. And this energy sequence has the oscillation of dark matter, so-called the frequency of omega.
Thank you. Once we have this theory about dark matter causing fundamental constants to oscillate, we have to go verify it experimentally to see if it actually has any basis in reality. Now, the way we do this is to measure the energy level of an electron at lots of different times, which you can express in terms of these two constants and which should also oscillate. And you can do this using something called spectroscopy. Basically, spectroscopy is the study of the properties of matter through its interaction with different frequencies of light. This is an example of the data from an absorption spectroscopy experiment. The supposedly fixed energy levels of the electrons in the atom determine which frequencies of light can be absorbed or emitted by electrons making jumps between different energy levels. But over time, the frequencies involved in these interactions, seen here in the position of the black lines, oscillate by a very small amount, and this lets us deduce the fractional change in the energy levels. And once we have our spectroscopy data, we need a way of extracting the frequency of that oscillation. Wally, heads up.
We're done with the spectroscopy, but is this enough? To understand the spectroscopy, we propose to use discrete Fourier transform. Not convinced? Well, let me explain. If you record a song and plot it in the time domain, it will look something like this. Oops. No information about the frequency, right? Well, don't worry. Let's take the Fourier transform of this time domain signal into the frequency domain, and ta-da! Not only have all the information about the frequency, but also significance of each frequency is pretty clear, as it is proportional to their respective amplitude of the frequencies. But wait, there is so much noise. How can we get rid of it? Well, I don't know, I'm out.
Don't worry, my friend, I got you. There are a bunch of different methods to reduce the noise pollution. And one of them is the autocorrelation method. Let's say we take a copy of our signal and we offset it by a tiny amount. Now we can take a look at how much of the offset signal is still similar to the original. In this case, not really much, right? Well, if we do this for many different offsets, we will soon notice a trend, which is that every time the offset is the same as the period length, we will have a spike in similarity because the two periods of the original and the offset part are on top of each other again. Now, here's the catch. Say we do the same thing with a signal that has one periodic part and one noisy part. If you do this many times again, you will see that the periodic part should exhibit exactly this behavior, but the noisy part should not. It should cancel each other out. So in the end, we get a much cleaner signal because not only does the autocorrelation method enhance the periodicity of the signal, no, it also reduces the noise pollution by a lot. So fear not, we are finally ready to find the exact frequency.
Now that I have the poster, the only thing we're missing is finding the frequency. Thanks to previous works, we have the high frequency feature detection method. It basically consists of 3 easy steps. We start with the autocorrelated or noisy signal. We get the Fourier transform of the signal. We smooth out the Fourier transform dependent on a delta parameter. And we finally numerically analyze the smoothed Fourier transform to find the most relevant peak. This allows us to retrieve the frequency of oscillation from a possibly noisy signal. And our tests indicate that it is able to detect the frequency even when the noise's standard deviation is a bit higher than the amplitude of the claim function, which is really good. Now that we detected the frequency, we need to find a way to express how sure we are that it is the correct one. This is done with the chi-squared function, a powerful tool in statistics that depends on the standard deviation of the Fourier transform and tells us whether a given point is a statistical fluke or not. As you can see in this graph, one peak stands out from the rest, and that corresponds to the correct frequency. With these tools, we were able to detect frequencies on the noisy signals and tell how confident we are about the oscillation being in the original clean signal. Now, we can go ahead to the conclusion.
Thanks, Emilio. So, in conclusion, we were able to extract frequency information from the Fourier transform of our data using autocorrelation to reduce noise. Then we were able to use high frequency feature detection and the chi-squared method to detect frequencies in the limited range up to 65 Hertz. There is an inverse frequency term in the amplitude, which means that the signal to noise ratio gets higher for lower frequencies and lower for high frequencies. In dedicated research undertaken by Weizmann scientists, some similar methods of data analysis were used to investigate possible candidates for dark matter. They used cesium vapor spectroscopy to investigate bosonic fields that couple to standard model particles and whether this would be a plausible candidate for dark matter.